Okay, let's take a quick look at simulating an inverter. We'll do this in LT-Spice. This is using the file MOS versus rswitch.asc that's available to you in the course documents. And then we'll do this also in CircuitLab. All right, so first off, this PMOS, NMOS transistor model. For this example, I'm using models that are really kind of from the book, or at least a book. A threshold for the NMOS in the model you can see down on the bottom in the dot model statement. The mu sub n in this case times COX and W over L are actually specified here of 430 and a threshold of 0.4 volts. This channel length is 130 nanometers or 0.13 microns, so this would really be a transistor on a chip. That's why this capacitor looks super small, 10 femtofarads, but it's a significant load for a transistor that is small. Also, just to orient ourselves, the power supply is 1.2 volts instead of 3.3 or 5 or something. All right, so we simulate this. Click the Run button. We're doing a transient simulation. If you look on the bottom of 2 nanoseconds, nothing's plotted, so I plot the input. We're just doing a square wave at the input. I plot the output, and we see some normal waveforms. In this region, so in this region right here, so the input is high, it goes low. When the input goes low, it's the CMOS switch that turns on. The input, the gate goes low. We do have a channel on the source side. We do have a channel on the drain side, or rather we don't. The output starts at low, climbs up, and goes from there. All right, we see it's fairly straight, and then it curves off. If I plot the drain current, over here and I plot the drain current, see how my mouse cursor changes just a little bit. I see a negative current. Let's see, I'm going to delete this and plot this on a plot the drain current. This way, it shows negative. I like to think as a positive number. What I did is I right-clicked on current. Got this expression, and I'm just going to stick a minus sign in there because I think of positive drain current as drain current that's going down. Flips the sign. Bigger. Okay, so it's 100 microamps as a peak. What I really want to point out here is this region from cursor 1 to cursor 2. So it's up here. In this little region, the drain current is constant. And in fact, from this spot down here on the voltage rising up, that is when the transistor truly is in saturation mode. Saturation mode, I'm using a very simple transistor model with these parameters. And in the simulator, this pulls really the textbook equations for MOSFET, the one that we use for hand calculations. At this point, so at point 2, let me put my cursor on out, cursor number 2 on the output, grab it here with my mouse, and I'm going to look at the drain current is constant, and when it goes off of constant, the voltage at the output node is, let's see, that's cursor 2 to V out. It is at 415 millivolts or so. I can use the arrow keys actually to scoot that around just a little bit. All right, so let's just say 400 millivolts. It looks like 400 is where off of constant current into triode mode. Well, if I look at the schematic during this situation, The drain voltage is at 400 millivolts. The input voltage is at 0 during that time, of course. The drain is higher than the input by 400 millivolts. If the drain is higher than that, that means the gate is more negative than the drain. As long as it's larger than the threshold voltage, this one, as long as it's larger than the threshold voltage, I do have a channel on the drain side. This is a PMOS, so that I need holes, free holes in the channel. The gate has to be negative. It's always 0. It means drain comes up. 400 millivolts, we switch from saturation mode to triode mode. And we can tell that in a lot of ways. One, by looking at this, the drain to source voltage is, or gate to drain voltage, large enough that we do have a channel on the drain side. I can also tell in the drain current for the MOSFET that it goes no longer constant and it decreases. Remember, it's a parabola, and as we get down here, our curves look exponential because they're going to converge to exponential as we go down. Okay, so let's delete this one. And I'm going to plot the drain current on the N axis up here. Plot the drain current on the N-type transistor. Oh, it's 200 microamps. Zoom in to this region here at around 1 nanosecond. And if you see, if we look at this, I'm going to turn on the marked data points. We see we get data points, not many data points, not many, and then a whole bunch during this transition time. Well, that's because the circuit simulator says, hey, there's a lot of stuff going on. I'm not quite so excited about, I'd like to see a few more data points in here, but you can see that it adaptively does that. As we go down, the transistor, this looks like it'd be nice and smooth. If this is an RC circuit, these data points would actually be spread way out because it is a true first order differential equation that describes it. This is not a first order differential equation. Remember, the really a quadratic, so the simulator really needs to says, hey, I need to do a good job and get lots of numbers here so I can be accurate. Again, up here I see the drain current is constant here, constant in this range, comes down, and the drain current goes down and off at this point. This is, I'm going to read 0.8 volts here. Well, 0.8 and 1.2, that's 0.4. My drain voltage, go back. So my gate voltage is red. My drain voltage is from high going to low. This is 400 millivolts. Well, if we look, the gate is 5, the drain is 400 millivolts below that. So at that moment is the threshold voltage. We hit the threshold voltage, and from here and below in voltage, the drain side of M1 also has a channel, and we switch into triode mode. Again, we can see this in two different places. One is the constant current, and then the other is just knowing what definition of threshold voltage is. Let's switch over to CircuitLab. Share this. It's not shared at the exact moment. This is a model of a BS170 and device model in CircuitLab. I just clicked on it, found it. It's the one that we're using. Just look at this a little bit. KP, or K prime. Squared, okay. V threshold at 0 or 0 8 volts. So 8 volts. The gate resistance in series with the gate, which is not relevant to us. RS and RD, these are resistances in series with the source and the drain. That does not include the channel. Capacitances, it's given the parameters that it's using pretty much our hand calculation model and nothing fancier. If we want more accuracy, we use a better model, but the better models have many more parameters. You just have to get the parameters either measuring yourself, which is a royal pain, or getting them from the manufacturer. ZVP3306, this transistor is quite close to the TP2106 that we used in lab. And sometimes we actually use this on sale. Okay, so 10 kilohertz, 100 nanofarad thing. I'm going to take out this inductor for a second. We'll run the simulation. All right. Simulation. Here, CircuitLab does not do the time steps automatically like LT-Spice does. This is a limitation. You have to get the time step correct. It needs to be small, but not too small. Small enough so that we can properly solve the differential equations that are not linear. But if it's too small, then we can't. Well, the simulation just takes forever. All right, let's zoom in on the rising edge output. CircuitLab's a little harder to read. Yes. Okay, so input is high, it goes low. The output was low, and then it's going to go high. It goes up, 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 and it goes, oops. How do we? Current act. Okay, output goes up. You can see I'm plotting the current. This is the current in the drain node of the transistor, NMOS, the PMOS transistor, because we're rising up. In this region right here, looking on the bottom, the drain current is constant. It's about 140 milliamps, and that's really what it is during your lab for the parts that we did. When the current goes non-constant or starts changing again, then that means our transistor goes into triode mode from saturation mode. At that point, we're at about 1.87 volts, 1.8 something volts, 1.82 volts. Looking here and then looking up here. Drain voltage, well, remember that was the threshold voltage of the CMOS MOSFET. Of course it is. All right. Constant current mode and then triode mode as we purge. If I plot the drain current in IM2D, actually I was plotting the capacitor current, which is either the PMOS current or the NMOS current. Okay, so run the simulation again. And we'll look at the falling edge. Oh. We notice the output voltage is decreasing. Well, there's negative current from the capacitor. That means current is going out of the capacitor or discharging it. In this region from 100 microseconds to 100.4 microseconds, I'm looking on the bottom, where the collector current, where the drain current is equal, constant. And you can see that the drop from here down to here, from gate voltage to drain voltage, is about the threshold voltage, 1.8 volts or something, I think the threshold was in this model. And we switch from triode mode or saturation mode to. What's actually interesting, it's always interesting, is we need to model the wires from our power supply. I'm going to take my power supply and scoot it over a little bit and stick an inductor in the top. I'm going to call this L wire plus. One in here. And I'll here. And what was I using for inductance? Use the all about circuits calculator. Diameter of the wire. What's the diameter of the wire? It's about 18 gauge wire. 18 AWG. 18 gauge is about 1 millimeter in diameter. I'll believe that. Right. All right, so 1 millimeter in diameter. The length of this wire, man, what? 30 centimeters? 30 centimeters. Calculate this, and I get 381 nanohenries of inductance. Okay. That's what it is. Let's just do 380 nanohenries. Remember, we have the negative wire from the power supply. We have to be really careful where we set our 0 here. Where we set our 0 volt reference depends on what voltages we're actually interested in. I'm interested in the voltages at my circuit, so I'm going to put my 0 volt reference right at my load. Because that's the output, it's the part that I care about. This wire part under here is all, by definition, the same voltage. And then these two inductors represent the red and the black wires that are going off to the power supply. Yeah, I said 30 centimeters long. That's what, 1.5 feet or 18 inches, something like that. 10, 12, 12-ish inches. It's kind of short. 30, 60. I don't know. We'll run with this. If you notice, I could slide, for the purposes of circuit analysis, I could put these two inductors in series, swap the order of L wire P, N, and the V supply. And as long as I don't need the voltages, the node voltages on the left side, I can do that. So the loop inductance, the total loop inductance is 760 nanohenries, but it's across two wires. Now VDD is not 5 volts. Cursor says it's 5 volts, but remember, an inductor at 0 or at DC is a short circuit. Let's simulate this again. Right. We get to wait briefly, and like actually nothing happened of too much. What I want to show is I want to plot the drain, the VDD of voltage. I'm plotting VDD. I can also edit this expression to put a minus sign there or something. That's fine. Actually, let's also plot the current delivered by the power supply. So this current would be positive when current's going up. Think of positive, power supply current is positive. So that's why I'm doing this. It's I supply negative. This one I'm going to delete that because I just want the power supply. Thinking about this for a second. And what do we have? Let's zoom in on our rising edge, because if you remember, the rising edge is where the action is for our voltage. All right, input goes high to low, output rises up. Our VDD, though, at this moment, VDD drops by about 1 volt. And then comes up. Well, remember, our current in that transistor, I should try to plot the inductor current. Need the voltage, I just want the inductance. Yeah, current. Probably a better way than running the simulation each time. Okay, so let's look at this. Zoom in. This stuff. And if we look at I wire LP, basically the same as the capacitors. It has to be KCL. That wasn't useful. Yeah, there's a little jagged here. That's because I'm not simulating enough data points here to get a nice glitch. I'm going to go from 0 to 100 microseconds. We're going to go down to 2 nanoseconds. Run this. This will take longer. 8 seconds to go. We'll fix this just like we did in the lab by adding a capacitor between the power supplies at the point of the load. Okay, so we have extra glitchy stuff. This is a really high frequency ring, so we even need to simulate this more data points right here. LT Spice will automatically add more data points. Great. But the point here is that the power supply voltage drops by a volt. That's because we went from 0 current to a large current, which is a very large dV or di dt, a change in current. That's voltage across this inductor. A wire P. All right, remember that drop there. I'm going to go back, we're going to add a capacitor to our power supply. And we called this the CS. Remember, this capacitor is very close to the inverter, and the long wire is going back to the power supply. Circuit simulator, we have to be really careful where the node. I'm going to go back to simulate. I'm going to do power supply current. Power supply. Capacitor current. Okay. Run the simulation. Let's see what we get. Of course. Runs in your browser, so the machine that you're running is the one that's doing the compute for the processing. Oh, this is terrible. We have no damping in here. Okay, let's look at VDD. Look right here, zoom in on the power supply voltage, and if you look at this, the power supply voltage does not droop at all. It droops over here. That's it. That's because the capacitor supplied all. Here is the capacitor current. Here's the load capacitance. Our signs are flipped, but you notice that all of the current charging my output load, which is the blue line, is coming from the CS capacitor, instead of having to flow through the wiring inductance. Which is exactly why we don't get a large di dt or a voltage across our wiring inductance right at this moment, right? Simulate these around. These wire inductances are actually probably a little low. Shorter wire. Okay. I have one more circuit here. This is a voltage controlled switch that LT Spice has. This is the same setup. These numbers are approximate on resistances from the data sheet. Simulate this thing. Well, howdy doody, I get the same behavior for the rising edge and the falling edge. But what I really get, I want you to pay attention closely to the current on here on the lower one. Current through the resistors, current through the capacitor and such, or current through the load. plot just the load current because only one of these switches is on at a time. If you see how the plus and the minuses are hooked up. Run this one more time. And if you notice, or if you remember, our current was flat for a little bit when the transistor was in saturation mode, and then it went exponential. This time, this capacitor current is exponential the entire time because it's just an RC circuit. We have an initial condition, it's 0, and then the output charges up through R2. Lots of things to say about this, but I'll share a link to this one. You can build it yourself. It's probably faster to build it yourself than find the link. And yeah, this is where it's nice to add wiring inductances and such into our circuit to see the effect. In lab, we saw more effects because more inductances and such in our circuit with our long loopy wire.